Tonight, we're going to explore one of humanity's most enduring dreams, the idea that one day we might leave Earth behind and begin again beneath the pale salmon skies of Mars. For more than a century, the red planet has occupied a remarkable place in our imagination. It has appeared in novels before spacecraft existed, in paintings before telescopes could reveal its true surface, and in scientific proposals long before rockets were capable of escaping Earth's gravity. Today, Mars is no longer simply a destination for fiction. It has become a genuine objective of space agencies, private companies, engineers, astronomers, and thousands of scientists working toward what was once considered impossible. To many people, colonizing Mars seems almost inevitable. If humanity hopes to survive for millions of years, surely we cannot remain confined to a single planet forever. A second home appears not merely desirable, but necessary. Mars, being relatively nearby and possessing familiar features such as mountains, valleys, polar ice, and a day only slightly longer than our own, naturally becomes the leading candidate. Yet the closer science examines Mars, the more complicated that confidence becomes. The planet is not simply another version of Earth waiting for new inhabitants. It is an entirely different world, shaped by billions of years of geological change, atmospheric loss, relentless radiation, and environmental conditions unlike anything humans have ever experienced. This raises a quieter and more profound question than whether we can reach Mars. It asks whether we truly understand what it would mean to live there. Throughout this journey, we will follow the evidence gathered by orbiters, landers, rovers, laboratory experiments, and decades of astronomical research. We will separate established science from engineering ambition, and careful prediction from hopeful speculation. Along the way, we will discover that the greatest challenge may not be building rockets powerful enough to cross interplanetary space, but understanding what makes a planet capable of sustaining a civilization. If you enjoy thoughtful explorations of astronomy and humanity's place in the universe, consider leaving a comment about whether you believe Mars should become our second home, and subscribe if you'd like to continue exploring these questions together. Our investigation begins not with distant futures, but with a much simpler question. Why has Mars captured the human imagination so completely, while countless other worlds have remained little more than points of light in the night sky? The answer begins with familiarity. Mars appears close enough to seem attainable, similar enough to feel welcoming, and mysterious enough to invite endless curiosity. But history often teaches us that familiarity can be deceptive. Sometimes the worlds that resemble our own most closely are also the ones that reveal with greatest clarity just how unusual Earth truly is. Before we decide whether colonizing Mars is a wise ambition or a costly mistake, we must first understand why generations of scientists came to believe that the red planet was humanity's best chance for another home. That story begins with the Mars we thought we knew. For most of human history, Mars was little more than a wandering point of reddish light crossing the night sky, unlike the steady stars. It drifted against the familiar constellations, drawing the attention of astronomers thousands of years before anyone understood what a planet truly was. Its distinctive color led many ancient civilizations to associate it with war, fire, and power. Yet beneath those cultural interpretations lay a simpler truth. Mars stood out because it was different. When the first telescopes turned toward the planet in the 17th century, that difference became even more intriguing. Observers could make out bright polar caps that seemed to grow and shrink with the seasons. Dark markings appeared to change over time, leading many to believe they were watching weather, vegetation, or even vast bodies of water, although later observations corrected many of these early conclusions. They planted a powerful idea in the scientific imagination. Mars did not look completely alien. It looked almost familiar. That impression has survived remarkably well into the modern era. Among all the worlds in our solar system, Mars remains the one that appears most Earth-like at first glance. It has a solid surface rather than crushing clouds or endless oceans of liquid hydrogen. It possesses mountains taller than any on Earth, enormous canyons stretching thousands of kilometers, frozen polar regions, changing seasons, dust storms, and a day lasting approximately 24 hours and 39 minutes. If an astronaut could somehow stand safely on its surface without needing to breathe, The rhythm of sunrise and sunset would feel surprisingly recognizable. Distance also plays a role in Mars's appeal. While millions of kilometers separate the two planets, Mars remains astonishingly close by cosmic standards. Depending on their positions in orbit, spacecraft can reach it in roughly 6 to 9 months using current propulsion technology. That journey is challenging, but it belongs within the realm of engineering rather than fantasy. By comparison, even the nearest star lies more than 4 light-years away, a distance so immense that no existing spacecraft could approach it within a human lifetime. Mars therefore occupies a unique position. It is distant enough to represent another world, yet close enough to feel achievable. Its size further strengthens this impression. Mars has about half the diameter of Earth and roughly 1/10 of its mass. Surface gravity measures only about 38% of what we experience here. A person weighing 70 kilograms on Earth would effectively weigh around 26 kilograms on Mars. Walking would require less effort. Jumping would feel effortless. Carrying heavy equipment would become easier. At first, these differences may even seem beneficial, but gravity influences far more than the simple act of walking. It shapes muscles, bones, circulation, balance, reproduction, and countless biological systems that evolved over billions of years under Earth's constant pull. Scientists have observed astronauts living aboard the International Space Station for months at a time, where prolonged exposure to microgravity causes bone density to decline, muscles to weaken, vision to change, and the cardiovascular system to adapt in unexpected ways. Exercise reduces these effects, but does not eliminate them. Mars offers more gravity than orbit, yet far less than Earth. No human has ever lived for years under Martian gravity, and no experiment has yet revealed how an entire lifetime, or multiple generations, would unfold under such conditions. The question remains open. Gravity is only the beginning. The Martian atmosphere presents a far greater challenge. Earth's atmosphere is both shield and life support system. It provides breathable oxygen, moderates temperature, distributes heat through weather, protects us from harmful radiation, and burns up countless meteoroids before they reach the ground. We rarely notice this invisible ocean of air because every human being has lived entirely within it. Mars possesses an atmosphere as well, but the comparison ends there. Its atmosphere is composed primarily of carbon dioxide, with only trace amounts of oxygen. More importantly, it is astonishingly thin. Less than 1% of Earth's atmospheric pressure at sea level. Standing on Mars, without a pressurized suit, would not simply leave someone unable to breathe. The pressure is so low that liquid water cannot remain stable for long on the surface. It either freezes or turns directly into vapor. This changes everything. On Earth, a glass of water can sit on a table indefinitely. On Mars, liquid water exposed to the open environment behaves according to entirely different physical rules. Any future settlement would need to create its own miniature Earth inside sealed habitats, carefully controlling pressure, temperature, humidity, and air composition every moment of every day. Temperature tells a similar story. Mars receives less sunlight because it orbits farther from the Sun. Average surface temperatures hover around -63 degrees Celsius, although conditions vary dramatically with location and season. Near the equator on a summer afternoon, temperatures may briefly climb above freezing. By night, they plunge once again into deep cold. Unlike Earth, Mars lacks thick oceans and a dense atmosphere capable of storing and redistributing heat. Days and nights swing between extremes, producing an environment that remains relentlessly unforgiving. Yet, despite all these obstacles, Mars continues to attract scientists for one remarkable reason. It was not always like this. Orbital imagery reveals dry river valleys winding across ancient landscapes. Vast sedimentary deposits resemble lakebeds. Minerals formed only in the presence of long-lasting water appear across the planet. Delta formations preserve the unmistakable signatures of rivers that once emptied into standing bodies of water billions of years ago. Mars seems to have possessed flowing water across significant portions of its surface. Where there is long-lived liquid water, scientists naturally ask another question. Could there also have been life That possibility transforms Mars from merely a destination into a scientific archive. It may preserve the history of a world that once approached habitability before losing it almost completely. Every rock examined by a rover, every mineral analysed by a laboratory, and every image returned from orbit contributes to understanding not only Mars's past, but also Earth's future and the evolution of rocky planets throughout the universe. For decades, this ancient history has inspired an optimistic belief. If Mars was once warmer, wetter, and perhaps even habitable, could humanity simply restore what nature took away? It is an appealing thought, elegant in its simplicity. But before asking whether Mars can become Earth again, we must first understand why it stopped resembling Earth in the first place. That question leads us to the first cracks in the familiar picture of the red planet. The image of Mars as humanity's future home rests upon a quiet assumption. If the planet once possessed rivers, lakes, and perhaps even a thicker atmosphere, then perhaps it simply needs a little help returning to that earlier state. The deserts appear dry, but they also appear ancient. The polar caps contain water ice. Beneath the surface, orbiting spacecraft have detected additional frozen reservoirs. To many people, Mars seems like an abandoned house. Dust has gathered over the furniture. The roof has begun to leak. But the structure itself still stands. Modern astronomy paints a more complicated picture. The more closely scientists have examined Mars, the less it resembles a neglected Earth, and the more it resembles a world that experienced a profound planetary transformation. To understand why, we must travel back more than 4 billion years, to a time when the solar system itself was still young. During its earliest history, Mars looked surprisingly promising. The Sun was fainter than it is today, yet Mars almost certainly possessed a much denser atmosphere than the one we observe now. Geological evidence suggests that rain may have fallen from clouds. Rivers carved valleys that remain visible from orbit. Water pooled inside impact craters, creating lakes that persisted for long periods. Entire drainage systems spread across the landscape, remarkably similar to those found on Earth. Some regions tell this story with extraordinary clarity. Ancient deltas display branching river channels that could only have formed through flowing liquid water over extended periods. Sedimentary rocks reveal layers deposited gradually, not by a single catastrophic flood, but through countless cycles of erosion and deposition. Clay minerals, discovered across wide areas by orbiting spacecraft and later confirmed by rovers on the ground, require prolonged interaction between rock and neutral liquid water. These discoveries changed an important scientific question. Astronomers no longer ask whether water ever existed on Mars. The evidence overwhelmingly indicates that it did. Instead, the question became far more difficult. Where did it all go? Some water still survives today. Brilliant white polar caps contain large quantities of frozen water mixed with frozen carbon dioxide. Radar instruments aboard orbiters have revealed additional ice buried beneath dust-covered plains, extending far beyond the visible poles. In some places, cliffs expose layers of nearly pure water ice, only a short distance below the surface. Yet this remaining water represents only a fraction of what ancient Mars appears to have possessed. The vanished atmosphere presents an even greater puzzle. Today, standing on Mars would feel almost like standing in a vacuum. Atmospheric pressure averages only about 6 millibars, compared with roughly 1,013 millibars at Earth's sea level. The Martian atmosphere is so thin that it provides almost no insulation, little protection from radiation, and almost no capacity to maintain stable liquid water on the surface. Something removed nearly all of it. Unlike Earth, Mars lacks a strong global magnetic field. Our planet's magnetic field is generated deep within its liquid outer core, where moving molten iron creates an enormous invisible shield extending far into space. This magnetic bubble, known as the magnetosphere, deflects much of the charged particle radiation constantly streaming outward from the Sun. Mars tells a different story. Measurements made by orbiters reveal scattered patches of magnetized crust, indicating that billions of years ago, the planet almost certainly possessed a global magnetic field as well. But at some point in its early history, the internal dynamo driving that field shut down. Scientists continue to investigate exactly why this happened. One possibility is that Mars, being much smaller than Earth, cooled more rapidly. As its interior lost heat, convection inside the core weakened until the magnetic field gradually disappeared. Without that protective shield, the upper atmosphere became directly exposed to the solar wind, a continuous stream of energetic particles flowing outward from the Sun at hundreds of kilometers per second. This interaction unfolded not over centuries, but over billions of years. Particle by particle, atom by atom, portions of the atmosphere escaped into space. The process is subtle enough that it cannot be witnessed directly by human eyes, yet modern spacecraft have measured it. NASA's MAVEN mission, which entered Martian orbit in 2014, was specifically designed to study the planet's upper atmosphere and its interaction with the solar wind. Its observations have shown that atmospheric particles continue escaping into space today. During periods of intense solar activity, this escape becomes significantly more rapid. Mars is still losing part of its atmosphere, not quickly enough for us to notice from year to year, but steadily enough to help explain how the thick atmosphere of ancient Mars gradually became the fragile remnant we observe today. This discovery carries an unsettling implication. Colonizing Mars is often described as building homes, growing crops, and constructing cities. But before any of those dreams can exist, settlers must first confront the fact that the planet itself is still shaped by the same processes that transformed it billions of years ago. Mars has not stopped being Mars. Dust storms illustrate this perfectly. Images returned by orbiters reveal storms that sometimes expand until they engulf nearly the entire planet. These events can last for weeks or even months, filling the atmosphere with fine particles that block sunlight, reduce temperatures, and interfere with solar-powered equipment. The dust itself presents another challenge. Martian dust is extraordinarily fine, produced over immense spans of time without rain, flowing rivers, or abundant vegetation to bind particles together. Electrostatic forces allow it to cling stubbornly to machinery, seals, joints, spacesuits, and scientific instruments. Engineers learned this lesson repeatedly during robotic missions. Solar panels gradually lost efficiency as dust accumulated. Mechanical components required careful protection. Cameras occasionally observed tiny whirlwinds, called dust devils, sweeping across the landscape, lifting reddish material thousands of meters into the air. For robotic explorers, these were engineering challenges. For permanent human settlements, they become questions of survival. Every airlock must function reliably. Every seal must remain airtight. Every life support system must continue operating despite years of exposure to abrasive dust that infiltrates nearly everything. Then there is the soil itself. At first glance, Martian soil appears similar to desert sand on Earth. Yet chemical analyses performed by landers and rovers revealed something unexpected. The regolith contains compounds known as perchlorates, salts that can interfere with human biology in sufficiently high concentrations. These chemicals complicate agriculture, water purification, and long-term habitation. Scientists are actively studying methods to remove or manage perchlorates, and research suggests they are not an insurmountable obstacle. But their presence reminds us that even the ground beneath future settlers' feet cannot simply be treated as ordinary Earth soil. Every familiar assumption requires reconsideration. Even the sky behaves differently. Because the atmosphere is so thin, sunlight scatters in unusual ways. During the day, the sky often appears butterscotch or salmon-coloured rather than blue. At sunset, however, something remarkable occurs. Fine dust suspended in the atmosphere scatters light so that the region immediately around the setting sun can briefly glow with soft blue tones. It is a beautiful reversal of Earth's sunsets, a small reminder that familiar experiences can unfold according to entirely different rules. Piece by piece, the simple vision of Mars begins to change. It is no longer merely a smaller Earth waiting for new inhabitants. It is the survivor of a planetary history that diverged from our own billions of years ago. Its rivers vanished. Its atmosphere thinned. Its magnetic shield disappeared. Its climate transformed beyond recognition. Yet, despite all these discoveries, much of what we know came not from human footsteps, but from tireless robotic explorers crossing landscapes no person has ever seen with their own eyes. Their journeys would reveal details that no telescope from Earth could ever uncover. And with each mission, the dream of colonizing Mars became both more realistic and more difficult than anyone had expected. For centuries, everything humanity believed about Mars came from a distance. Astronomers watched it through telescopes as it drifted across the night sky. Larger instruments revealed brighter details. Better cameras produced sharper images, yet even the finest observatories on Earth were still looking across tens of millions of kilometers. Mars remained a world interpreted through blurred light and careful deduction. That began to change during the space age. Instead of asking what Mars looked like from afar, humanity decided to visit it. The first attempts were extraordinarily difficult. Reaching another planet required far more than simply building larger rockets. Spacecraft had to survive launch, navigate millions of kilometers through interplanetary space, arrive at precisely the correct moment, and operate in an environment no machine had previously experienced. Many early missions failed. Navigation errors, launch problems, communication failures, and technical malfunctions reminded engineers that crossing the gap between planets was unlike any previous form of exploration. Yet each unsuccessful mission contributed knowledge that made the next attempt more reliable. In 1965, NASA's Mariner 4 spacecraft achieved one of the first truly transformative milestones. As it flew past Mars, it transmitted only a handful of images by modern standards. The photographs arrived slowly, line by line, requiring hours to reconstruct. Yet what they revealed immediately challenged decades of expectation. Instead of forests or canals, Mariner 4 showed a cold landscape covered with impact craters. The surface looked surprisingly similar to the Moon. Many scientists wondered whether Mars had always been a frozen desert. Public optimism about finding a living world faded almost overnight. But Mariner 4 had seen only a tiny fraction of the planet. Subsequent missions expanded the picture. Mariner 9 became the first spacecraft ever to orbit another planet in 1971. Ironically, when it arrived, Mars was hidden beneath one of the largest global dust storms ever observed. For weeks, the spacecraft could see almost nothing except a reddish haze. The delay proved unexpectedly valuable. As the storm gradually settled, immense features slowly emerged from the dust. Gigantic volcanoes rose above the clouds. One mountain towered nearly 22 kilometers above the surrounding plains. Today, we know it as Olympus Mons, the largest volcano in the solar system. Nearby, another astonishing feature stretched across the landscape. Valles Marineris, named after the spacecraft itself, extended more than 4,000 kilometers in length. In places, it reached depths approaching 7 kilometers. It dwarfed Earth's Grand Canyon, not simply in size, but in geological complexity. Mars was no longer a small lunar world. It possessed a dramatic geological history unlike anything previously imagined. Orbital photographs also revealed winding valleys that looked unmistakably familiar. These channels branched like river systems on Earth. Some began in highlands, before descending into ancient basins. Others terminated in broad fan-shaped deposits, resembling river deltas. Water had almost certainly shaped them. The debate shifted once again. Mars was neither an Earth-like paradise nor merely a lifeless moon. It appeared to be something far more intriguing, a planet that had changed. Yet orbiters could answer only certain questions. To understand the chemistry of rocks, the composition of soil, or the properties of the atmosphere near the surface, scientists needed to land. That challenge proved even greater. Entering the Martian atmosphere is often described by engineers as navigating the 7 minutes of terror. A spacecraft approaches the planet at tremendous speed. The atmosphere is too thin to slow it as effectively as Earth's, yet thick enough to generate intense heat during entry. Every second requires carefully timed events. Heat shields, parachutes, retro rockets, airbags, or sky cranes must all function perfectly. There is no opportunity for human intervention. Radio signals require many minutes to cross the distance between Earth and Mars. By the time mission controllers receive confirmation that entry has begun, the spacecraft has already landed safely or been destroyed. Mars demands complete autonomy. The Viking missions of 1976 became the first successful American landers to operate on the Martian surface. Their objectives extended far beyond photography. Scientists hoped they might answer one of humanity's oldest questions. Is there life on Mars? Viking carried biological experiments specifically designed to detect signs of microbial activity within Martian soil. The results proved both fascinating and frustrating. Some experiments produced chemical reactions that initially appeared promising. Others failed to detect organic molecules expected if life were present. Over time, most researchers concluded that the observed reactions could be explained by unusual soil chemistry rather than living organisms. The findings did not eliminate the possibility of ancient or hidden life. They simply showed that no clear evidence of active biology had been detected at the landing sites. Once again, Mars resisted simple answers. The following decades brought remarkable advances in robotic exploration. Instead of stationary landers alone, engineers developed vehicles capable of travelling across the surface. The first successful rover, Sojourner, arrived in 1997 as part of the Pathfinder mission. Although modest in size, it demonstrated that mobile exploration could dramatically expand scientific investigation. Larger rovers soon followed. Spirit and Opportunity landed in 2004 on opposite sides of the planet. Designed to operate for 90 Martian days, both dramatically exceeded expectations. Spirit explored for more than 6 years. Opportunity continued working for nearly 15 years before finally falling silent during another global dust storm in 2018. Their discoveries transformed scientific understanding. Layered rocks recorded ancient environments shaped by water. Minerals formed only under wet conditions appeared repeatedly. Evidence accumulated that some regions of ancient Mars had once possessed lakes, groundwater, and chemical conditions potentially suitable for microbial life. The dream of finding past habitability became stronger than ever. Then came curiosity. Landing inside Gale Crater in 2012 using an entirely new sky crane system, Curiosity carried a sophisticated laboratory capable of performing detailed chemical analyses. It climbed the lower slopes of Mount Sharp, a mountain built from billions of years of layered sediments. Each layer represented another page in Mars's environmental history. Curiosity discovered organic molecules preserved within ancient rocks. It identified environments that could once have supported microbial life. Importantly, organic molecules are not themselves evidence of biology. They can form through entirely non-biological processes as well. Scientists carefully distinguished between these possibilities. The discovery did not prove life had existed. It demonstrated that some of the necessary chemical ingredients were present. More recently, Perseverance has continued this investigation inside Jezero Crater, the site of an ancient river delta, selected because it offers one of the best opportunities to search for signs of ancient microbial ecosystems. Unlike previous rovers, Perseverance is collecting carefully chosen rock samples intended for eventual return to Earth by future missions, where laboratories far more advanced than anything that can be placed aboard a spacecraft may study them. Nearby, another remarkable milestone unfolded. The small helicopter Ingenuity demonstrated powered flight on another planet for the first time. Its flights were brief, yet historically significant. A world once visible only as a reddish point of light had become a place where aircraft could fly. Each robotic mission deepened our knowledge. Each also quietly reshaped the argument for human settlement. Early visions imagined that astronauts would arrive to discover Mars. Instead, robots have already performed much of that first exploration. They have mapped the terrain, measured radiation, analyzed rocks, studied weather, and identified promising resources. Ironically, every new discovery has made Mars simultaneously more familiar and more demanding. We now know far more about the planet than earlier generations ever imagined. And precisely because we know more, we also recognize how many hidden difficulties remain. The photographs are breathtaking. The science is extraordinary. But transforming these discoveries into a place where human beings can safely live requires confronting a much deeper question. What does survival actually mean on a world where every breath, every sip of water, every meal, and every degree of warmth depends entirely upon technology? That is where our investigation now turns. A photograph of Mars can be strangely deceptive. From orbit, broad plains glow beneath the afternoon sun. Layered cliffs cast long shadows across ancient valleys, frost glitters around the poles. A distant horizon stretches beneath a pale sky that feels almost familiar. Remove the spacesuit from an astronaut standing in such an image, and the scene could almost be mistaken for a remote desert on Earth. The illusion lasts only until we begin asking a simple question. What would an ordinary day actually be like? Not the dramatic moment of landing, not the first footsteps, not the celebration broadcast around the world, just an ordinary Tuesday. 5 years after the colony has been built, you wake, not because sunlight enters your bedroom, but because an artificial clock tells you morning has arrived. Outside your window lies a landscape where opening the front door without protection would be fatal within moments. Every breath you take has been manufactured by machines. Every drop of water has been recycled, purified, measured, and recycled again. Every degree of warmth surrounding your body exists because countless systems continue operating exactly as designed. The habitat is not simply your home, it is your entire environment. On Earth, we rarely notice how generously our planet supports us. Air surrounds us without effort. Water falls from the sky. Gravity shapes our bodies from birth. Plants grow in ordinary soil beneath sunlight filtered through a thick atmosphere. Countless microorganisms recycle nutrients beneath our feet. Entire ecosystems quietly perform the work required to sustain civilization. Mars provides almost none of these services. Everything must be recreated. Consider something as ordinary as breathing. An average adult consumes roughly 500 litres of oxygen every day. Inside a Martian settlement, oxygen cannot simply be stored indefinitely. Transporting enough compressed oxygen from Earth for a permanent colony would quickly become impractical. Instead, settlers would need continuous production. Fortunately, Mars offers possibilities. Carbon dioxide makes up about 95% of the Martian atmosphere. Instruments such as the small MOXIE experiment carried aboard NASA's Perseverance rover have successfully demonstrated that oxygen can be extracted from this carbon dioxide through electrochemical processes. The achievement was significant. MOXIE proved that oxygen production on Mars is scientifically possible, but there is an important distinction. Producing a few grams of oxygen for an engineering demonstration differs enormously from supplying hundreds of people every hour of every day for decades. Scaling laboratory success into reliable, civilization-scale infrastructure is one of the greatest challenges in engineering. Every life support system requires redundancy. Every backup requires another backup. Failure cannot simply be inconvenient. It becomes existential. Water presents another equally demanding challenge. Mars certainly contains water, primarily locked within ice deposits beneath the surface and at the poles. Future settlements would almost certainly mine these frozen reserves. Ice could be melted, purified, divided into hydrogen and oxygen through electrolysis, used for drinking, hygiene, agriculture, fuel production, and industrial chemistry. In principle, this sounds reassuring. In practice, every stage requires energy. Excavating frozen ground demands heavy equipment. Heating ice consumes power. Purification systems require maintenance, pumps, filters, storage tanks, and pipelines must continue functioning through years of dust exposure and extreme temperatures. Water becomes less a natural resource than an industrial product. Nothing arrives freely. Food introduces an even more complex problem. The first human missions will almost certainly rely heavily on supplies transported from Earth. Freeze-dried meals, packaged ingredients, and preserved foods are well understood after decades of spaceflight. Permanent settlements cannot depend upon that approach forever. Cargo launch from Earth remains expensive, limited and vulnerable to delays. A self-sustaining colony would eventually need to produce much of its own food. Research conducted aboard the International Space Station and in terrestrial simulation habitats has demonstrated that plants can grow under carefully controlled conditions. Artificial lighting, hydroponic systems, nutrient recycling, and enclosed greenhouses offer realistic methods for producing vegetables and other crops. Yet agriculture on Mars is unlike farming anywhere on Earth. Natural sunlight is weaker because Mars orbits farther from the Sun. Dust storms can reduce available light even further for weeks at a time. Martian soil, or regolith, lacks the living microbial ecosystems that enrich Earth's farmland. It also contains perchlorate salts that must be managed before many crops could be safely cultivated. Future greenhouses may therefore resemble highly automated laboratories more than traditional farms. Every variable must be measured: temperature, humidity, carbon dioxide, nutrient concentrations, water flow, lighting cycles, pollination. Even small failures could threaten food production for an entire settlement. Energy underlies all of these systems. Without electricity, life support stops. Water freezes. Air circulation ceases. Communications fail. Heating disappears. Unlike Earth, where regional power failures can often be offset through neighbouring electrical grids, an isolated Martian colony would possess no external infrastructure. Its power systems must be exceptionally reliable. Solar panels represent one possibility. Mars receives roughly 43% as much sunlight as Earth. Under clear conditions, solar energy remains entirely usable, and robotic missions have relied upon it successfully for decades. But robotic missions also revealed its limitations. Dust gradually accumulates across panel surfaces, reducing efficiency. Global dust storms can dramatically decrease available sunlight for extended periods. Engineers can design cleaning systems and larger solar arrays, yet these solutions increase complexity and maintenance requirements. For this reason, many mission planners also consider nuclear power an attractive option. Compact nuclear reactors can generate continuous electricity independent of weather or daylight. Several designs are currently being studied for future deep space missions. No single solution has yet emerged as universally accepted. Most realistic settlement concepts combine multiple energy sources to improve resilience. Even with reliable electricity, another challenge remains: temperature. Mars is cold enough that maintaining comfortable indoor conditions requires constant heating. Heat lost through habitat walls must be continuously replaced. Every doorway, every airlock, every connection between modules becomes part of an intricate thermal system, balancing survival against limited energy resources. Outside conditions remain unforgiving. Pressure suits become everyday clothing whenever work extends beyond the habitat. These suits must protect against vacuum-like pressure, ultraviolet radiation, abrasive dust, and severe cold while still allowing delicate manual tasks. Burrowing a communications antenna, installing scientific instruments, inspecting pipelines, mining ice, constructing new habitats. Every outdoor activity becomes a carefully planned engineering operation. Distance from Earth introduces still another complication. When astronauts orbit Earth aboard the International Space Station, communication delays are almost imperceptible. Mars changes that relationship completely. Depending upon the positions of the two planets, radio signals require between roughly 4 and 24 minutes to travel one way. A simple conversation becomes impossible. Questions cannot receive immediate answers. Emergency instructions cannot arrive instantly. Future settlers must operate with remarkable independence. Mission control becomes less a supervisor than a distant advisor. Psychology, therefore, becomes almost as important as engineering. Human beings evolved within vast living ecosystems, rich with changing weather, flowing rivers, forests, oceans, birdsong, insects, and countless subtle experiences rarely noticed until absent. Mars offers none of these. The landscape changes slowly. Vegetation exists only inside habitats. Fresh air never touches your face. Rain never falls. No natural sound carries across the plains, because the atmosphere itself is so thin. Researchers conducting long-duration isolation experiments on Earth consistently find that confinement, routine, limited social interaction, and prolonged separation from home present significant psychological challenges. Future Martian settlers would likely experience these stresses, while also knowing that returning to Earth may not be immediately possible. Technology can preserve life. It cannot automatically replace every aspect of living. This realization brings us to the heart of our investigation. Most discussions about colonizing Mars focus on transportation. How large should the rockets be? How many people should travel first? How quickly can habitats be assembled? Yet the evidence gathered over decades suggests that transportation may prove to be only the beginning. Reaching Mars is an engineering problem. Remaining there for generations may be something far more difficult. For every human need that Earth provides effortlessly, Mars demands an artificial substitute. The deeper we examine the practical realities of settlement, the more another question quietly emerges. If an entire civilization depends upon uninterrupted technology every minute of every day, has humanity truly colonized a new world, or merely built a fragile island of Earth inside an environment that remains fundamentally hostile? For centuries, the word colony has carried a simple image. It suggests permanence, a place where people do not merely visit, but settle. Children are born there. Communities expand. Roads appear, followed by schools, workshops, observatories, gardens, and eventually entire cities. At some point, the settlement no longer feels temporary, it becomes home. When we speak about colonizing Mars, we often carry this familiar picture with us. Yet modern planetary science asks us to pause before accepting it. What does permanence actually mean on a world that cannot naturally support human life? This is the first great mystery at the heart of our journey. It is not whether human beings can survive on Mars for weeks or months. Decades of spaceflight suggest that. With sufficient engineering, they probably can. The deeper question is whether a civilization can remain there indefinitely without depending upon Earth. The distinction is subtle but profound. A research station in Antarctica demonstrates that people can endure one of Earth's harshest environments. Scientists live there through months of darkness, severe cold, and isolation. Supplies arrive by carefully planned expeditions. Sophisticated equipment maintains warmth, electricity, communications, and medical care. No one would describe Antarctica as self-sustaining. Every station remains connected to a much larger civilization beyond the ice. Mars would begin in much the same way. The first habitats would rely heavily upon cargo delivered from Earth. Replacement electronics, medical equipment, specialized machinery, computer components, scientific instruments, and countless manufactured parts would arrive aboard regular missions. Eventually, however, every vision of a permanent Martian civilization reaches the same turning point. The supply ships must become less important. Otherwise, Mars remains not a second home, but a remote outpost. This transition is known among engineers and mission planners as in situ resource utilization, often shortened to ISRU. The concept is straightforward. Instead of transporting everything across interplanetary space, settlers learn to use local materials. Water comes from Martian ice. Oxygen comes from the atmosphere. Building materials come from local rock. Fuel is manufactured on Mars rather than launched from Earth. Every kilogram produced locally saves many kilograms that would otherwise need to leave Earth's deep gravity well. The logic is compelling. It is also extraordinarily difficult. Consider something as ordinary as replacing a broken valve. On Earth, the solution is often simple. Manufacture another one. Purchase one. Ship one overnight. On Mars, every replacement depends upon industrial capabilities that may not yet exist. To manufacture even a small mechanical component requires raw materials, refined metals, precision tools, machine shops, quality control systems, trained technicians, and reliable energy. Those factories require their own equipment. That equipment requires replacement parts. Those parts require still more factories. The chain continues backward until it reaches an uncomfortable realization. Modern civilization is astonishingly interconnected. Very few products are created entirely within a single city, or even a single country. A smartphone contains materials mined on several continents. Medical equipment relies upon global supply chains. Computer chips require manufacturing facilities of extraordinary complexity. Even simple medicines often depend upon ingredients produced in multiple countries. Earth supports this complexity because billions of people participate in one enormous industrial network. Mars would begin with perhaps a few dozen settlers, eventually hundreds, perhaps one day thousands. That raises an important economic question. How many people are actually required before a civilization becomes self-sustaining? Scientists, economists, and systems engineers do not yet agree. Some studies suggest that technological self-sufficiency may require populations far larger than most early colony proposals envision. Others argue that advanced automation, robotics, and additive manufacturing could dramatically reduce the necessary population. The debate remains active because no human settlement has ever attempted anything comparable. History offers only partial guidance. Every isolated community on Earth, no matter how remote, has still existed beneath a breathable sky, within a functioning biosphere, and surrounded by accessible natural resources. Mars removes all three advantages simultaneously. Biology presents another layer of uncertainty. Human beings evolved over millions of years within Earth's environment. Gravity remained constant. The atmosphere remained stable. The magnetic field shielded life from much of the sun's radiation. Microorganisms filled every handful of soil and every breath of air. Mars changes nearly every one of these conditions. One concern involves reproduction. Scientists understand surprisingly little about how pregnancy, fetal development, childhood growth, and lifelong health would proceed under Martian gravity. No mammal has ever completed multiple generations under 38% of Earth's gravity. Experiments aboard space stations have provided valuable information about cells, embryos, insects, fish, rodents, and other organisms exposed to reduced gravity or microgravity. Many biological systems continue functioning. Some behave differently. Development, bone formation, immune responses, balance, and muscle growth may all be influenced by gravity in ways that remain incompletely understood. Mars occupies an unexplored middle ground. Its gravity is neither Earth's nor weightlessness until human beings actually live there across generations. Some questions simply cannot be answered. Radiation deepens the mystery. Earth enjoys two remarkable forms of protection. Our magnetic field deflects many charged particles arriving from space. Our atmosphere absorbs much of the remaining radiation before it reaches the surface. Mars possesses neither protection at comparable levels. Measurements collected by the Curiosity rover during its journey to Mars, along with observations from surface instruments and orbiting spacecraft, indicate that astronauts traveling to and living on Mars receive significantly greater radiation exposure than people on Earth. Long-term exposure increases the probability of cancer and may also affect the nervous system, cardiovascular health, and other biological processes. Engineers have proposed several methods of protection. Habitats may be buried beneath layers of Martian soil. Natural lava tubes could provide substantial shielding. Water storage tanks might surround living quarters because water absorbs radiation effectively. These approaches appear scientifically promising, yet they also illustrate an important point. The safest Martian cities may not resemble cities at all. They may exist largely underground. When popular culture imagines glass domes beneath open skies, reality points toward reinforced structures covered by meters of rock. Safety often requires sacrificing beauty. Medical care introduces another challenge. A hospital on Earth depends upon specialists, diagnostic equipment, laboratories, pharmaceutical manufacturing, emergency transportation, and rapid consultation with experts around the world. A Martian settlement would possess only limited resources. Complex surgery, organ transplantation, advanced cancer treatment, emergency evacuation. Many capabilities taken for granted on Earth would be unavailable or significantly constrained. Communication delays eliminate real-time assistance. Medical teams would require exceptional independence. Every colonist would likely receive broader emergency training than is common today. The settlement itself would become a carefully balanced ecosystem where every individual plays multiple roles. Then there is failure on Earth. Infrastructure occasionally stops working. Power outages occur. Pipelines break. Communication networks fail. Usually, surrounding regions compensate until repairs are completed. Mars offers no surrounding civilization. A prolonged failure of oxygen production, water recycling, heating, or power generation could threaten every inhabitant simultaneously. Engineers therefore speak constantly about redundancy. One oxygen generator becomes two become four. Critical systems operate independently whenever possible. Maintenance becomes continuous rather than occasional. Reliability becomes a way of life. This is not pessimism. It is engineering. The goal is not to eliminate risk completely, because that is impossible. The goal is to understand risk honestly. At this point, the central mystery becomes much clearer. Can humanity build habitats on Mars? Most scientists would answer that this appears technically achievable. Can humans survive there for months? Perhaps years? Evidence suggests they probably can. Can Mars eventually host a permanent civilization independent of Earth? That question remains unanswered. It is here that scientific discussion becomes especially careful. Some researchers believe advances in robotics, artificial intelligence, manufacturing, and resource utilization will gradually overcome today's limitations. Others argue that biological constraints, economic realities, and environmental hazards may prove far more difficult than technological optimism assumes. Neither position has yet been confirmed by experience. No human settlement on another planet has ever existed. Every prediction extends beyond direct observation. Science, therefore, distinguishes between demonstrated capability and reasonable expectation. The distinction matters because when discussions about Mars become overly optimistic or excessively pessimistic, they often move beyond evidence. The most valuable approach remains following the data wherever it leads. Fortunately, the data are improving every year. Orbiters continue measuring atmospheric escape. Rovers continue studying geology. Radiation instruments continue recording conditions on the surface. Engineers continue testing habitats, life support systems, and resource extraction technologies. Piece by piece, observation replaces assumption. And, as the evidence accumulates, it allows us to examine one question with increasing precision. What do we actually know about the risks of living on Mars, and which dangers remain matters of careful scientific inference rather than certainty? That evidence will guide the next stage of our journey. Science advances most confidently when it measures rather than assumes. For much of history, Mars inspired ideas that could not easily be tested. Some observers imagined vast civilizations hidden beneath its reddish surface. Others pictured a world that merely awaited human settlers. Both visions were shaped more by imagination than by evidence. Modern exploration has gradually changed that balance. Today, every major discussion about living on Mars begins not with hope or doubt, but with measurements collected by spacecraft, landers, rovers, laboratory experiments, and decades of engineering research. The central question is no longer, what might Mars be like? Instead, it has become, what do we actually know? Perhaps the clearest example concerns radiation. On Earth, most people rarely think about radiation arriving from space because our planet quietly protects us. High above the atmosphere, Earth's magnetic field diverts many charged particles emitted by the Sun. Those that continue inward encounter nearly 100 kilometers of atmosphere, where countless collisions absorb much of their energy before it reaches the ground. Mars provides far less protection. Measurements collected during NASA's Mars Science Laboratory mission, which carried the Curiosity rover to the planet, allowed scientists to estimate the radiation astronauts would receive during the journey itself. Instruments continued recording conditions after landing, providing one of the most complete pictures yet of the Martian radiation environment. The results confirmed what researchers had long expected. Both the voyage through deep space and life on the Martian surface expose humans to substantially more radiation than everyday life on Earth. This does not mean astronauts would immediately become ill. Radiation exposure is cumulative. The concern lies in what repeated exposure may do over many years. Increased lifetime cancer risk remains one of the primary considerations, although researchers also continue studying possible effects on the cardiovascular system, the central nervous system, and long-term cognitive health. There is encouraging news as well. Radiation is not an unsolvable problem. Matter blocks radiation. The thicker the shielding between a person and energetic particles, the lower the exposure generally becomes. Water, polyethylene, and Martian soil all provide useful protection. Computer models suggest that habitats buried beneath several meters of regolith could reduce radiation significantly compared with structures left exposed on the surface. Yet this immediately introduces another engineering challenge. Excavating, transporting, and placing thousands of tons of soil over living quarters requires heavy machinery operating reliably in one of the harshest environments ever encountered. The evidence therefore leads naturally from one problem to another. Measurements reveal the hazard. Engineering must provide the solution. Dust offers another example. At first glance, Martian dust appears harmless. After all, deserts exist on Earth. Sand blows across dunes every day without threatening civilization. Martian dust behaves differently. Its particles are extraordinarily small, often finer than ordinary terrestrial sand. Without abundant liquid water and biological activity to bind them together over geological time, these particles remain loose and highly mobile. Robotic missions have repeatedly demonstrated how persistent the dust can be. It settles onto cameras. It accumulates on instruments. It works its way into joints, seals, and mechanical systems. Laboratory studies using Martian dust simulants on Earth suggest that repeated exposure may accelerate wear on equipment designed for long-duration missions. For human settlements, the concern extends beyond machinery. Fine dust can also enter habitats during routine operations unless carefully controlled. Some particles may irritate lungs if inhaled, while the perchlorate compounds identified in Martian soil require careful handling because prolonged exposure to high concentrations can interfere with thyroid function. Researchers continue studying practical methods to remove dust before astronauts re-enter living spaces. Airlocks may include advanced cleaning systems. Spacesuits may remain attached outside habitats rather than being carried indoors. Electrostatic technologies are being investigated to repel dust from surfaces. None of these ideas eliminate the challenge entirely, they simply reduce it. Water availability has also become much clearer through direct observation. Early spacecraft hinted at frozen water near the poles. Modern orbiters, equipped with radar instruments, have greatly expanded that understanding. Large deposits of underground ice exist across many regions of Mars, sometimes lying surprisingly close to the surface. This discovery fundamentally changed mission planning. Transporting all necessary water from Earth would be extraordinarily expensive. Mining local ice appears far more practical. Yet measurements also reveal important limitations. Some deposits lie beneath thick layers of rock. Others occur in regions that experience extremely low temperatures or difficult terrain. Extracting usable water remains technically feasible, but location matters enormously. Future settlement sites will almost certainly be selected as much for accessible resources as for scientific interest. Power generation follows a similar pattern. Researchers have accumulated decades of experience operating solar-powered spacecraft on Mars. The results are mixed. Solar panels work well under favorable conditions. They also gradually lose efficiency as dust accumulates. Opportunity survived for nearly 15 years in part because occasional dust devils unexpectedly cleaned its solar panels, restoring much of their performance. Engineers welcomed these fortunate events. They could not depend upon them. Global dust storms remain another important factor. These storms do not generate hurricane-force winds like those on Earth because the Martian atmosphere is so thin. Even fast-moving air carries relatively little force. Instead, their greatest impact comes from blocking sunlight across enormous regions. For weeks, sometimes months, available solar energy can decline dramatically. This evidence has strengthened interest in compact nuclear reactors for future human missions. Unlike solar arrays, nuclear systems continue producing electricity regardless of weather, season, or daylight. Scientists and engineers continue evaluating different combinations of power sources, recognizing that resilience often comes from diversity rather than dependence upon a single technology. Gravity presents one of the most difficult questions because direct evidence remains limited. We know exactly how strong Martian gravity is. We know precisely how humans respond to Earth's gravity. We also possess extensive data describing prolonged exposure to microgravity aboard space stations. What we lack is long-term evidence for the environment between those two extremes. Scientists therefore rely upon careful inference. Bone loss observed in orbit suggests reduced gravity influences skeletal health. Muscle atrophy provides similar clues. Animal studies offer additional information. Computer models attempt to predict long-term outcomes. Yet none of these approaches can completely substitute for decades of human experience on Mars itself. This uncertainty is scientifically significant. It reminds us that absence of evidence is not evidence of safety, nor is it evidence of danger. It simply marks the boundary where observation has not yet reached. Psychology presents another area where evidence continues to grow. Unlike radiation detectors or weather stations, human emotions cannot be measured with a single instrument. Instead, researchers study analog environments. Antarctic research stations, submarine deployments, long-duration space missions, isolation experiments such as NASA's High Seas Habitat in Hawaii, and other international simulation programs. Across these diverse settings, certain patterns appear repeatedly. Isolation affects mood. Limited social groups can experience tension. Monotony influences motivation. Communication delays complicate relationships with people far away. Most participants adapt remarkably well. Some struggle more than others. The evidence suggests that psychological resilience may become just as important as engineering expertise when selecting future Martian crews. Finally, there is perhaps the most encouraging body of evidence: human adaptability itself. History repeatedly demonstrates that people learn to thrive in environments once considered impossible. Polar regions, High mountains, deep oceans, orbit around Earth. Each frontier demanded new technologies, new habits, and new forms of cooperation. Mars may become another chapter in that story, or it may reveal limits we have not previously encountered. The evidence alone cannot answer that question. It can only define what must be overcome. By now, one conclusion has become increasingly clear. Living on Mars is not prevented by a single overwhelming obstacle. Instead, it involves dozens of interconnected challenges, each scientifically understandable, each technically demanding, and each influencing all the others. Radiation affects habitat design. Habitat design affects energy requirements. Energy requirements influence settlement location. Location determines water availability. Water supports agriculture. Agriculture shapes population growth. Every decision echoes throughout the entire system. It is precisely this complexity that has led scientists and engineers to develop very different visions for how a permanent Martian civilization might eventually emerge. Some believe the obstacles can be overcome gradually through advancing technology. Others argue that certain environmental realities may remain fundamentally limiting. The evidence itself does not choose between these possibilities. It simply provides the foundation upon which every serious theory must stand. And those competing ideas are where our journey now leads. Once the evidence has been gathered, science enters a quieter phase. Observation tells us what exists. Theory attempts to explain what those observations mean. Engineering asks what can be built despite them. The conversation surrounding Mars has gradually shifted into this territory. Few scientists now argue about whether Mars is cold, dry, or exposed to significant radiation. Those measurements are well established. The real debate concerns something much larger. Given everything we know, what is the most realistic path toward a permanent human presence? There is no single answer. Instead, several broad approaches have emerged, each grounded in science to varying degrees, each attempting to solve the same problem from a different direction. The first approach is also the most conservative. Rather than speaking of cities or civilizations, it envisions Mars primarily as a scientific frontier. In this view, the earliest settlements resemble expanded research stations. Scientists, engineers, physicians, geologists, and technicians would rotate between Earth and Mars over carefully planned missions. Habitats would remain relatively small. Supplies would continue arriving from Earth, although increasing amounts of water, oxygen, and fuel would be produced locally. This concept requires the fewest assumptions. It builds directly upon decades of experience operating space stations in orbit and research bases in Antarctica. Most planetary scientists consider some version of this scenario highly plausible. Its strength lies in caution. Every new capability is demonstrated before becoming essential. Every expansion follows successful experience. Its weakness is equally clear. A research outpost is not a self-sustaining civilization. If regular transportation from Earth were interrupted for long enough, the settlement could face severe difficulties. The second approach aims much higher. Instead of remaining dependent upon Earth, settlers would gradually construct a largely self-sufficient industrial society. Mining operations would extract metals, factories would manufacture replacement parts, greenhouses would provide food, local resources would produce water, oxygen, fuel, plastics, glass, and construction materials. Over many decades, dependence upon imported supplies would steadily decline. This vision has attracted considerable interest because it aligns with one of humanity's oldest patterns. Throughout history, isolated settlements have gradually learned to use local resources rather than relying entirely upon distant homelands. Yet Mars differs from every previous frontier. Early colonies on Earth still possessed breathable air, fertile ecosystems, flowing water, familiar gravity, and living soils. Mars begins without any of these advantages. The scientific question therefore becomes one of scale. Can automation, robotics, artificial intelligence, and advanced manufacturing compensate for environmental conditions unlike any humans have previously faced? Some researchers believe they can. Others remain more cautious. The disagreement reflects uncertainty rather than contradiction. No comparable settlement has ever existed. Another proposal moves much of the colony underground. At first glance, this may sound disappointing. Popular illustrations often depict transparent domes overlooking spectacular landscapes beneath open skies. The evidence, however, points elsewhere. Several meters of Martian soil provide substantial radiation shielding. Underground temperatures remain more stable than those on the surface. Natural lava tubes, formed billions of years ago by flowing volcanic rock, may offer enormous protected spaces requiring relatively little excavation. Orbital imagery has identified numerous candidate lava tubes across Mars. Some entrances appear large enough to accommodate substantial habitats. Scientists do not yet know the internal condition of most of these structures. Future robotic missions may eventually explore them. If they prove stable, they could become attractive locations for early settlements. This concept enjoys considerable scientific support because it relies upon naturally existing geological features rather than attempting to transform the entire planet. Its limitation is psychological. Living primarily beneath the surface may reduce radiation exposure dramatically. It also reduces direct contact with the landscape that inspired the journey in the first place. Another idea has captured public imagination more than almost any other: terraforming. The word itself sounds almost poetic. To terraform means to alter an entire planet until it more closely resembles Earth. Instead of constructing isolated habitats, humanity would gradually transform the Martian environment itself. The atmosphere would become thicker, temperatures would rise, liquid water would return to the surface. Eventually, perhaps even plants could grow outdoors. It is one of the most ambitious engineering concepts ever proposed. It is also one of the most misunderstood. From a scientific perspective, terraforming remains a hypothesis rather than an established engineering plan. Researchers have explored many possible mechanisms: releasing greenhouse gases trapped beneath the surface, producing powerful artificial greenhouse gases, redirecting icy bodies from the outer solar system, deploying enormous orbital mirrors to increase surface warming, generate artificial magnetic shielding to reduce future atmospheric loss. Each proposal addresses one part of the problem. None solves all of it. More importantly, several studies suggest that Mars may simply lack enough readily accessible carbon dioxide to produce a thick, Earth-like atmosphere using currently known resources. This conclusion does not prove terraforming impossible forever. It indicates that, based upon present evidence, the task appears vastly more difficult than early, optimistic estimates suggested. The distinction matters. Science separates physical possibility from practical feasibility. An idea may not violate the laws of physics while still remaining beyond foreseeable technological capability. Terraforming currently occupies that uncertain territory. Some researchers have proposed an even more focused alternative. Rather than changing the entire planet, why not create local environments, pressurized cities, large enclosed valleys, connected greenhouse complexes, artificial ecosystems extending gradually outward from protected centers? This approach dramatically reduces the amount of atmosphere that must be maintained while allowing many Earth-like conditions inside. In essence, instead of transforming Mars into Earth, humanity would bring carefully controlled pieces of Earth to Mars. Many engineers consider this significantly more realistic than planetary-scale terraforming, yet it still depends upon continuous technological maintenance. Then there is another perspective altogether. Some scientists argue that the primary value of Mars is not settlement, it is knowledge. Mars preserves geological records from the earliest history of rocky planets remarkably well because it lacks active plate tectonics and extensive surface erosion. Its ancient rocks may contain clues about planetary evolution, climate change, and perhaps even the earliest stages of life. Large-scale colonization, if not carefully managed, could complicate this scientific record. Human activity inevitably introduces contamination. Microorganisms accompany explorers despite extensive sterilization procedures. Construction alters landscapes. Mining disturbs geological formations. For this reason, planetary protection remains an important area of discussion. Scientists continue debating how best to balance exploration with preservation. If indigenous microbial life, living or fossilized, exists anywhere on Mars, protecting that evidence becomes one of humanity's greatest scientific responsibilities. This debate illustrates an important principle. Colonization is not purely an engineering decision. It is also an ethical one. How should humanity treat another world? Should Mars primarily become a laboratory, a settlement, a protected natural archive? Different scientific communities emphasize different priorities. None possesses a universally accepted answer. One final idea deserves attention: because it influences nearly every discussion about Mars. The concept of becoming a multi-planetary species. Supporters argue that establishing permanent settlements beyond Earth reduces the long-term risk of civilization-ending catastrophes. Large asteroid impacts, global pandemics, extreme climate change, supervolcanic eruptions, future technological disasters. If humanity exists on multiple worlds, they argue, our species becomes more resilient. Many scientists agree with the general logic. At the same time, others point out an important limitation. Early Martian settlements would likely remain heavily dependent upon Earth for many decades. If civilization on Earth experienced a truly global collapse before Mars achieved substantial independence, the colony itself might struggle to survive. The timing therefore matters. Simply placing humans on Mars does not automatically guarantee long-term security. By the end of this debate, one conclusion stands out. No serious scientific proposal describes Mars as an easy destination. The disagreements concern strategy, timescale, technology, economics, and priorities, not the difficulty itself. Facts remain facts. Evidence remains evidence. Ecocide theories describe the Martian environment with increasing confidence. Hypotheses explore future possibilities. Speculation begins only where observation currently ends. Among all these competing ideas, one possibility emerges as especially intriguing. Suppose humanity succeeds. Suppose the engineering challenges are overcome. Suppose a permanent settlement truly begins to flourish beneath the Martian sky. What kind of civilization would gradually emerge on a world that shaped every aspect of human life differently from Earth? That question carries us beyond engineering and into the future that science allows us to thoughtfully explore. For a moment, let us set aside the question of whether humanity can establish a permanent settlement on Mars. Instead, we will consider a different question. What if we do, not through wishful thinking or cinematic fantasy, but by following a future that remains broadly consistent with today's scientific understanding? The distinction is important. Everything that follows is a thought experiment grounded in accepted physics, current engineering trends, and observations already discussed. Where the evidence ends, we will identify the uncertainty rather than presenting possibility as fact. The first permanent settlement would almost certainly begin modestly. Perhaps a handful of interconnected habitat modules stand partially buried beneath Martian soil. Airlocks connect laboratories, sleeping quarters, medical facilities, workshops, and greenhouses. Outside, robotic vehicles move slowly between solar arrays, excavation sites, communication towers, and ice mining equipment. From orbit, the settlement is almost invisible. There are no towering skyscrapers, no illuminated highways, only a few carefully protected structures separated by a vast landscape that remains almost exactly as it has for billions of years. Life inside unfolds according to rhythms unlike those on Earth. The Martian day, known as a sol, lasts approximately 39 minutes longer than an Earth day. That difference seems insignificant at first, yet over weeks and months it gradually shifts daily schedules away from those followed by friends and family back on Earth. Communication windows, scientific operations, and maintenance routines begin to follow the planet's own quiet rhythm. A new calendar slowly emerges. The settlers still remember Earth, but their lives are increasingly shaped by another world. Children born on Mars, if that eventually becomes medically feasible, would experience something even more profound. Their first steps would occur in gravity only 38% as strong as Earth's. Their muscles, balance, and coordination would develop under conditions no human evolution ever anticipated. Scientists cannot yet predict exactly how lifelong development would unfold. Some physiological adaptations may prove beneficial. Others may require medical intervention. Until direct evidence exists, these possibilities remain open scientific questions. One consequence appears highly plausible. Returning to Earth after spending many years on Mars could become physically difficult. Even today, astronauts returning from months aboard the International Space Station often require rehabilitation as their bodies readjust to Earth's gravity. Mars offers more gravity than orbit, but substantially less than Earth. A person who has spent decades there may find Earth's stronger gravitational pull exhausting. Bones, muscles, the cardiovascular system all may require lengthy adaptation. For some individuals, permanent return could prove impractical. Without intending it, humanity may eventually create populations whose home is no longer Earth. Culture would evolve alongside biology. The first settlers would likely carry customs, languages, holidays, and traditions from many nations over generations. However, daily experience begins reshaping identity. Shared challenges often create shared culture. The sound of air recycling through habitat walls, the routine inspection of pressure seals, the celebration of each successful harvest inside greenhouse modules, the arrival of cargo spacecraft after months of waiting. These experiences have no direct equivalent on Earth. Gradually, they become normal. History offers many examples of isolated communities developing distinctive traditions within only a few generations. Mars would almost certainly do the same. Language itself may change. Technical vocabulary becomes part of ordinary conversation. New expressions emerge from experiences unique to the planet. Even familiar directions acquire new meaning. Instead of speaking casually about the weather outside, people might ask about radiation forecasts or dust conditions before leaving the habitat. Daily life adapts to the environment that surrounds it. Economics would also change. Early settlements would depend heavily upon supplies from Earth. Over time, local industries gradually expand. Water extraction, construction, scientific research, manufacturing, maintenance, software development, perhaps one day even specialized exports. Yet Mars presents an unusual economic challenge. Transport remains expensive. Any product shipped between planets must justify the enormous energy required to move it. This suggests that information, scientific discoveries, advanced engineering, and intellectual work may become more valuable than bulk physical goods. Knowledge travels at the speed of light. Cargo does not. Another consequence follows naturally. Autonomy. Communication delays prevent immediate decision-making from Earth. If an emergency occurs, local leaders must respond independently. As settlements grow larger, governance gradually becomes more local. History again provides a useful comparison. Communities separated by great distances often acquire increasing political independence over time because local circumstances require local decisions. Mars would amplify this tendency, not because of conflict, but because physics itself limits communication. A conversation delayed by 20 minutes each way cannot support moment-by-moment administration. Psychological adaptation may prove equally significant. Researchers studying long-duration isolation frequently observe an interesting phenomenon. People gradually stop comparing their surroundings to home. Instead, they begin accepting their environment as normal. Future Martian settlers may experience something similar. The reddish landscape becomes familiar. Pressure suits become ordinary clothing for outdoor work. Artificial lighting replaces changing weather as the background of everyday life. The extraordinary slowly becomes routine. Yet some aspects of Earth may remain impossible to replace. Open oceans, natural forests, wind moving through leaves, birdsong at dawn, the scent of rain. These experiences arise from an enormously complex biosphere built over billions of years. Even sophisticated habitats may reproduce only small parts of that living system. This raises an unexpected philosophical question. What defines a home? Is it the planet beneath your feet, the people around you, the culture you inherit, or the environment that shaped your species? Science cannot answer such questions. It can only describe the circumstances in which they arise. Another possibility deserves careful consideration. Suppose Mars succeeds beyond every expectation. The settlement grows from dozens of people to hundreds, from hundreds to thousands. Eventually, perhaps tens of thousands. Would the colony continue expanding indefinitely? Not necessarily. Unlike Earth civilizations, Martian growth would remain tightly linked to available energy, water, industrial capacity, food production, and habitat construction. Population growth may therefore proceed more deliberately than throughout much of human history. Every new resident requires measurable increases in life support capacity. Expansion becomes an engineering calculation as much as a demographic one. This may produce a society unusually conscious of limits. On Earth, many natural systems quietly absorb mistakes. Mars offers far less margin for error. Waste must be recycled, resources monitored, infrastructure maintained continuously. Failure affects everyone. Some researchers speculate that such conditions could encourage exceptionally cooperative social structures. Others caution that isolation and resource constraints might instead create new forms of tension. Both possibilities remain speculative because no comparable society yet exists. Perhaps the most remarkable consequence concerns perspective. From Mars, Earth becomes another planet in the sky, bright, blue, small. Its phases change as the two worlds move through their orbits. Children raised on Mars may one day look toward that distant point of light with the same curiosity that many people on Earth now reserve for Mars. Home changes direction. This thought experiment reveals something surprising. Even if every major engineering challenge is overcome, colonizing Mars does not simply reproduce Earth somewhere else. It creates something entirely new, a civilization shaped by different gravity, different sunlight, different geography, different risks, different rhythms of communication, different relationships with nature. Mars would not merely change humanity. Humanity would also change Mars, however carefully. The interaction would reshape both, and that realization leads us toward an even broader perspective. For the question of whether Mars is the right destination cannot be answered by studying Mars alone. To understand its true significance, we must place it within the much larger story of how planets evolve throughout the universe, and why Earth may be far more unusual than its familiarity allows us to notice. For thousands of years, Mars and Earth were often treated as siblings. They circle the same star. They formed from the same swirling cloud of gas and dust approximately 4.6 billion years ago. Both are rocky planets with mountains, volcanoes, impact craters, polar ice, and evidence of ancient geological activity. At first glance, they appear to be variations on a common theme. The deeper astronomy investigates, however, the more remarkable their differences become. Those differences extend far beyond our solar system. They reveal something fundamental about the nature of habitable worlds. Planetary scientists often describe Earth as residing within the Sun's habitable zone, the range of distances where temperatures may allow liquid water to exist on a planet's surface under the right atmospheric conditions. Mars also lies near the outer edge of this region. That simple fact has inspired generations of optimism. If Mars occupies the habitable zone, why did it become a frozen desert while Earth remained a living world? The answer is more complex than distance alone. Habitability is not a single condition. It is the product of many interacting systems operating together over immense spans of time. Earth possesses abundant liquid water. So did ancient Mars. Earth has an atmosphere. Mars still has one, although it is much thinner. Both planets contain carbon, oxygen, hydrogen, nitrogen, and many of the chemical ingredients associated with life. Yet somewhere during their early histories, their evolutionary paths separated. Understanding that divergence has become one of the central goals of planetary science. The comparison begins beneath the surface. Earth remains geologically active. Its interior still retains enormous amounts of heat left over from planetary formation, radioactive decay, and ongoing processes deep within the mantle and core. This internal energy drives plate tectonics. Continents drift. Ocean floors spread. Volcanoes recycle material from the planet's interior. Carbon moves continuously between rocks, oceans, the atmosphere, and living organisms through what geologists call the long-term carbon cycle. This cycle acts as a powerful climate regulator. Over millions of years, increasing volcanic activity can replenish atmospheric carbon dioxide. Chemical weathering removes carbon from the atmosphere and stores it within rocks. While the process operates far too slowly to influence everyday weather, it helps stabilize Earth's climate over geological timescales. Mars tells a quieter story. Its smaller size allowed internal heat to escape more rapidly. Most evidence suggests that large-scale geological activity diminished much earlier than on Earth. Without active plate tectonics comparable to Earth's, Mars gradually lost one of the major processes capable of recycling gases between its interior and atmosphere. Exactly how important this difference proved remains an area of active research. Scientists continue refining models describing the interaction between volcanic history, atmospheric evolution, and planetary cooling. Another contrast involves magnetic protection. Earth's magnetic field extends tens of thousands of kilometers into space, forming a vast protective envelope around the planet. While not perfect, it significantly reduces the direct impact of the solar wind on our atmosphere. Mars appears to have lost its global magnetic field billions of years ago. As discussed earlier, this likely contributed to the gradual erosion of its atmosphere. The comparison illustrates an important lesson. Habitability depends not only upon where a planet is located, it also depends upon what occurs deep inside it. Astronomers have discovered thousands of planets orbiting distant stars during the past few decades. Many resemble Earth in size, others resemble Mars. Some orbit within the habitable zones of their stars, yet determining whether any of them truly support stable, long-term environments remains extraordinarily difficult. A planet may possess the correct temperature. It may still lack an atmosphere. Another may possess an atmosphere, but experience intense stellar radiation. A third may have abundant water while orbiting a star prone to violent flares, capable of repeatedly stripping away atmospheric gases. Habitability therefore emerges not from one favourable condition, but from the interaction of many. Mars serves as one of our best natural laboratories for studying this complexity. Its history demonstrates that rocky planets can change dramatically. A world that once supported rivers may eventually become almost completely dry. A thick atmosphere may become thin. A warmer climate may cool. These transitions are not merely interesting historical events. They help astronomers interpret observations of distant exoplanets whose surfaces remain far beyond direct exploration. Every lesson learned from Mars improves our understanding of worlds orbiting other stars. Earth also appears differently when viewed through this broader perspective. Because we have never lived anywhere else, it is easy to regard Earth's environment as ordinary. Astronomy suggests the opposite. A planet possessing long-term liquid oceans, active geology, a stable atmosphere, a protective magnetic field, moderate climate, and an extraordinarily rich biosphere may represent a remarkably uncommon combination of circumstances. Scientists continue debating how common such worlds truly are. The data remain incomplete. Thousands of exoplanets have been discovered. Only a tiny fraction can currently be studied in sufficient detail to estimate atmospheric composition. Future telescopes may eventually detect gases associated with biological activity on distant planets. Even then, interpretation will require great caution. Many atmospheric chemicals can arise through non-biological processes. Mars reminds researchers never to confuse intriguing evidence with definitive proof. Another cosmic connection emerges through time. The Sun itself is changing. Like every star, it evolves. Over billions of years, its brightness slowly increases as nuclear fusion gradually alters its internal structure. The change is extremely slow by human standards. Nevertheless, astronomical models indicate that Earth's climate will become progressively less hospitable over immense future timescales. Long before the Sun reaches the end of its life, Mars, receiving less sunlight, may experience different long-term climatic evolution. Some have suggested that as the Sun brightens over billions of years, Mars could eventually become more temperate. This idea remains scientifically interesting, but should be placed in context. These changes occur over timescales vastly exceeding the duration of human civilization. They do not solve the engineering challenges discussed throughout this documentary. Instead, they illustrate that planetary habitability itself is dynamic rather than permanent. Worlds evolve. Stars evolve. Entire planetary systems evolve. Human history occupies only a tiny moment within these immense processes. This broader perspective also reshapes the original question. Perhaps the greatest significance of Mars is not that it offers humanity another place to live. Perhaps it offers something equally valuable. A second example. With only one inhabited planet, it is difficult to determine which characteristics of Earth are essential and which are accidental. Mars provides a comparison. A world similar enough to illuminate differences, yet different enough to reveal how many conditions must align before a planet becomes continuously habitable. In that sense, Mars functions almost like a control experiment conducted by nature itself over billions of years. The comparison grows even more compelling when we examine other members of our own solar system. Venus, despite being similar in size to Earth, evolved into an intensely hot world with a crushing carbon dioxide atmosphere. The icy moons Europa and Enceladus conceal global oceans beneath frozen crusts. Titan possesses rivers and lakes, although they are composed of liquid methane and ethane rather than water. Each world demonstrates a different outcome of planetary evolution. Mars occupies a unique position among them. It is neither comfortably habitable nor completely inaccessible. It exists near the boundary where familiar conditions give way to profoundly different ones. That boundary teaches humility. It reminds us that creating or preserving a habitable world may require an intricate balance that cannot easily be reconstructed once lost. As planetary science has advanced, another surprising realization has gradually emerged. Many of the processes that transformed Mars also help scientists understand Earth's own future: climate stability, atmospheric evolution, and resilience. The stories of the two planets are no longer separate. They are deeply connected. And those unexpected connections may ultimately reveal why colonizing Mars is not simply about escaping Earth, but about understanding it. For much of the 20th century, Earth and Mars were often studied as separate worlds. Geologists examined Earth's mountains, oceans, and continents. Planetary scientists investigated Martian volcanoes, craters, and deserts. The two fields occasionally overlapped, but they largely followed different paths. Over the past few decades, that separation has gradually disappeared. Today, researchers increasingly recognize that understanding one planet often depends upon understanding the other. Mars has become a mirror, not because it reflects Earth's present, but because it preserves clues that Earth itself has long since erased. Our planet is remarkably active. Wind wears away mountains. Rain transports sediments into rivers. Glaciers reshape entire landscapes. Plate tectonics recycles the crust back into the mantle. Volcanoes bury ancient surfaces beneath younger rock. Life itself constantly transforms the chemistry of the surface. These processes make Earth dynamic and habitable. They also erase history. Very little of Earth's original crust remains intact after more than 4 billion years. Mars experienced far less geological recycling. Without active plate tectonics comparable to Earth's and with much weaker erosion, enormous regions of its ancient surface have survived almost unchanged for billions of years. In a sense, Mars functions as a planetary archive. Its oldest rocks preserve chapters of solar system history that Earth can no longer provide. This connection has transformed how scientists study the origin of planets. When researchers investigate ancient river deltas on Mars, they are not simply asking whether water once flowed there. They are also asking how young rocky planets evolve, how atmospheres develop, how climates stabilize or collapse, how long habitable environments can persist. Every answer helps refine models describing Earth's earliest history. One of the most surprising examples involves impact craters. Earth was heavily bombarded during the earliest history of the solar system. Asteroids and comets struck with extraordinary frequency. Most of those ancient craters have vanished through erosion and tectonic recycling. Mars still preserves many of them. By counting crater densities across different regions, scientists estimate the relative ages of Martian landscapes. Those measurements help calibrate geological timescales used throughout planetary science. Even our understanding of Earth's ancient bombardment benefits from observations made hundreds of millions of kilometers away. Water provides another unexpected connection. At first glance, Mars appears to tell a story about loss. Dry riverbeds, empty lake basins, frozen polar caps. Yet these features also reveal how water behaves under different planetary conditions. Researchers compare Martian valleys with terrestrial river systems. They examine sediment layers deposited in ancient lakes. They analyze minerals that form through prolonged interaction with liquid water. These comparisons improve climate models used not only for Mars, but also for Earth's distant past. The relationship works in both directions. Studies of Earth's deserts help scientists interpret Martian dunes. Volcanic fields in Iceland resemble certain lava plains observed on Mars. The hyper-arid Atacama Desert in Chile serves as a testing ground for robotic instruments searching for subtle chemical signatures. Antarctica provides insights into ice dynamics under extremely cold conditions. No place on Earth perfectly reproduces Mars. Together, however, these analog environments allow researchers to test equipment, validate theories, and refine exploration strategies before spacecraft ever leave our planet. The connection extends beyond geology into biology. Life on Earth has demonstrated astonishing adaptability. Microorganisms thrive in acidic lakes, deep underground, inside Antarctic ice, near hydrothermal vents, and within intensely dry deserts. These organisms, known collectively as extremophiles, have transformed scientific thinking. Rather than asking whether life can exist only under comfortable conditions, Researchers now investigate the full range of environments biology can tolerate. This shift has profound implications for Mars. Ancient Mars almost certainly possessed environments far more hospitable than today's surface. If microbial life ever emerged there, could some traces remain preserved beneath the ground? Could dormant microorganisms survive in isolated subsurface niches? No convincing evidence currently supports either possibility. Yet the existence of extremophiles on Earth broadens the range of environments scientists consider worthy of investigation. Again, Earth reshapes how we search Mars. Mars reshapes how we understand Earth. Atmospheric science offers another remarkable parallel. Researchers studying Mars have developed increasingly sophisticated computer models describing dust circulation, seasonal weather patterns, and atmospheric escape. Many of the mathematical techniques used in these simulations also contribute to climate modeling on Earth. While the two planets differ enormously, the underlying physics of fluid motion, energy transfer, and atmospheric dynamics follows the same fundamental laws. Planetary science rarely advances in isolation. Insights gained from one world often illuminate another. Perhaps the most profound connection concerns planetary resilience. Earth has experienced dramatic climate changes throughout its history. Ice ages advanced and retreated. Continents shifted. Mass extinctions reshaped ecosystems. Asteroid impacts altered global environments. Volcanic eruptions changed atmospheric chemistry. Despite these upheavals, Earth's biosphere repeatedly recovered. Mars appears to have followed a different path. Whether because of its smaller size, the loss of its magnetic field, declining volcanic activity, atmospheric escape, or a combination of many factors, the planet crossed environmental thresholds from which it did not naturally return. Scientists continue debating the relative importance of each process. What remains clear is that planetary systems can change profoundly over geological time. That lesson extends well beyond Mars. Astronomers now know that planetary evolution is common throughout the galaxy. Worlds are not static. They develop. They transform. Sometimes they become more hospitable, sometimes less. Understanding those pathways has become one of the great scientific challenges of our century. Another unexpected connection emerges through technology. Many innovations developed for Mars ultimately find applications on Earth. Advanced water recycling systems, autonomous robotics, efficient food production in controlled environments, compact medical diagnostics, improved habitat engineering. These technologies arise because Mars demands extraordinary efficiency. Resources cannot be wasted. Energy must be carefully managed. Recycling becomes essential rather than optional. Ironically, solutions designed for another planet may prove valuable on our own as humanity confronts growing environmental and resource challenges. The exchange works both ways. Every improvement in terrestrial engineering strengthens future exploration. Every improvement in planetary exploration enriches life on Earth. This reciprocal relationship challenges a common assumption. Mars exploration is often portrayed as an escape plan. Scientific reality suggests something rather different. Studying Mars repeatedly teaches us how unusual, interconnected, and resilient Earth's systems truly are. Rather than encouraging us to abandon our home, the red planet continually reveals why that home is so precious. The comparison becomes even more meaningful when viewed from orbit. Astronauts frequently describe a psychological experience known as the overview effect. Looking back at Earth from space, national borders disappear. The atmosphere appears astonishingly thin. The entire biosphere occupies only a fragile layer surrounding a single planet. Mars reinforces this perspective. Its dry valleys and silent plains remind us what a rocky planet can become when many protective systems no longer operate together. That does not mean Earth is destined to follow Mars. The planets differ in important ways. Their histories are not identical. Their futures need not converge. Science does not support such a simplistic conclusion. Instead, Mars teaches a subtler lesson. Habitability is not guaranteed. It emerges from the interaction of countless physical processes operating over immense spans of time. The more deeply astronomers investigate these relationships, the more they appreciate how much remains to be discovered. Every new mission to Mars answers some questions while creating others. Every improved climate model reveals additional complexity. Every geological sample uncovers another chapter in a story that is still incomplete. These growing connections have guided a new generation of exploration. Rather than sending spacecraft simply to photograph Mars, modern missions seek to understand it as an evolving planetary system. They combine orbiters, rovers, helicopters, laboratories, supercomputers, and international collaboration in ways unimaginable only a few decades ago. The result is an increasingly detailed portrait of the red planet. Yet with every advance, the frontier of knowledge moves just a little farther away. If the first half-century of Mars exploration was devoted to reaching the planet, the present era is devoted to understanding it. The questions have become more precise. How quickly is the atmosphere still escaping into space? Where are the largest accessible deposits of water ice? Which ancient rocks are most likely to preserve evidence of past habitability? How much radiation reaches different regions of the surface? Can oxygen and fuel truly be produced using local resources? Each question demands instruments far more sophisticated than those carried by the earliest spacecraft. Modern Mars exploration has therefore become an international scientific effort involving orbiters, landers, rovers, laboratories, computer simulations, and planning for future human missions. Each contributes a different piece of the puzzle. From hundreds of kilometers above the surface, orbiters provide the broadest view. They map mineral deposits, measure seasonal changes, track dust storms, study atmospheric composition, search for underground ice, monitor weather across the entire planet. Unlike rovers, which examine a single location in extraordinary detail, orbiters reveal how local discoveries fit into the larger planetary picture. One of the most valuable achievements of orbital exploration has been the identification of widespread subsurface ice. Radar instruments have shown that frozen water exists beneath many regions previously thought to be relatively dry. For future explorers, this information is more than scientifically interesting. It directly influences where settlements might eventually be established. A location rich in accessible ice could dramatically simplify life support systems, agriculture, and fuel production. Yet the maps also reveal complexity. Some promising ice deposits lie in latitudes where winter temperatures become especially severe. Other regions possess favorable sunlight but less accessible water. Selecting future landing sites therefore becomes an exercise in balancing many competing priorities. Robotic explorers on the surface provide a different kind of knowledge. Curiosity continues climbing through the layered rocks of Mount Sharp inside Gale Crater. Each geological layer represents a different chapter in Martian environmental history. By analyzing minerals, sedimentary structures, and chemical compositions, scientists reconstruct changing climates that occurred billions of years ago. These investigations have revealed repeated transitions between wetter and drier conditions. Rather than a planet that changed only once, Mars appears to have experienced a more complicated environmental evolution than earlier models suggested. Perseverance has expanded this investigation even further. Operating inside Jezero Crater, it explores an ancient river delta where flowing water once entered a standing lake. On Earth, river deltas are excellent locations for preserving microscopic evidence of ancient life because sediments settle gradually, burying organic material under favorable conditions. Scientists selected Jezero for precisely this reason. The rover carries instruments capable of analyzing rocks at extremely fine scales, searching for textures and chemical signatures that may indicate past habitable environments. An important distinction must be maintained. Perseverance has not discovered ancient Martian life. Instead, it is identifying the most scientifically valuable samples for eventual return to Earth. This sample return strategy represents one of the most significant developments in planetary science. Laboratories on Earth are vastly larger and more capable than anything that can currently be transported to another planet. Advanced microscopes, high-precision mass spectrometers, isotope laboratories, sophisticated chemical imaging systems. Together they can perform analyses impossible aboard a rover. For this reason, scientists increasingly view carefully selected rock samples as one of the greatest scientific treasures Mars can offer. Returning those samples remains technically challenging. Multiple spacecraft, complex orbital rendezvous, and strict planetary protection procedures would all be required. Plans continue evolving as engineers refine mission architectures. While timelines have shifted over the years, the scientific motivation remains exceptionally strong. If successful, return samples could reshape our understanding of early Mars for decades. Modern exploration has also expanded into the atmosphere itself. Orbiters continue monitoring how the solar wind interacts with the upper atmosphere, improving models of atmospheric escape. Researchers now possess much more detailed observations than were available only a generation ago. These data help explain not only Mars's history, but also the evolution of planetary atmospheres throughout the galaxy. Exoplanet scientists frequently incorporate lessons learned from Mars into models describing distant rocky worlds orbiting other stars. Computer simulations have become equally important. Today's planetary models combine enormous amounts of observational data with advances in computational power. Researchers simulate atmospheric circulation, dust transport, groundwater movement, ancient climates, ice stability, radiation environments, potential landing trajectories, even the operation of future habitats. These simulations do not replace observation. They organize existing evidence into coherent physical models that can be tested against new discoveries. Whenever spacecraft return additional data, scientists compare those observations with predictions. Agreement strengthens confidence. Disagreement often leads to entirely new questions. Artificial intelligence has begun contributing in more subtle ways. Machine learning systems assist researchers by identifying geological patterns across vast collections of orbital imagery, classifying terrain, detecting fresh impact craters, and helping prioritize locations worthy of closer investigation. Importantly, these systems do not replace scientific judgment. They accelerate the analysis of datasets far too large for humans to examine manually. The result is a more efficient search for meaningful patterns hidden within millions of observations. Engineering research has advanced alongside scientific exploration. On Earth, laboratories continuously test technologies intended for future human missions. Closed-loop life support systems recycle water with extraordinary efficiency. Experimental habitats evaluate long-duration living conditions. Advanced spacesuits improve mobility while reducing dust contamination. Three-dimensional printing explores the possibility of manufacturing tools and structural components using local materials. Small-scale oxygen production experiments demonstrate the practicality of using Martian carbon dioxide as a resource, rather than treating it solely as an obstacle. None of these technologies alone enables colonization. Together they gradually reduce uncertainty. Another area receiving increasing attention is autonomous robotics. Future human explorers are unlikely to arrive first. Instead, robotic systems may prepare landing sites years in advance. They could deploy power systems, excavate protective berms around habitats, begin extracting water ice, assemble communication infrastructure, even manufacture simple construction materials before astronauts ever leave Earth. This approach reflects an important lesson learned from decades of Mars exploration. Robots and humans perform different tasks exceptionally well. Robots tolerate radiation, vacuum, and extreme temperatures without life support systems. Humans remain unmatched in flexibility, creativity, and complex decision-making. Most realistic exploration strategies therefore combine both. Perhaps the most remarkable feature of modern Mars research is not any single discovery. It is the gradual disappearance of isolated disciplines. Geologists collaborate with atmospheric scientists. Biologists work alongside chemists. Engineers consult psychologists. Astronomers compare Mars with distant exoplanets. Computer scientists contribute to rover navigation and planetary mapping. Mars has become a meeting place for many branches of science. Every discovery echoes across multiple fields. Yet, despite all these advances, modern astronomy has also revealed something deeply humbling. The more precisely we understand Mars, the more clearly we recognize the limits of our knowledge. Every improved map uncovers new geological mysteries. Every refined climate model exposes additional uncertainties. Every promising rock sample raises new questions about ancient environments. Science advances not by eliminating mystery, but by making the mysteries increasingly precise. That realization brings us naturally to the next stage of our journey, for even after decades of exploration, some of the most important questions about Mars remain unanswered. Not because scientists have failed, but because nature has proven even more intricate than we expected. The most important discoveries in science often begin with a realization, not that we have found the answer, but that the question is deeper than we first understood. Mars has followed this pattern repeatedly. Each generation of explorers has arrived with more advanced instruments, more detailed theories, and more ambitious goals. Each has returned with extraordinary discoveries: ancient rivers, buried ice, complex minerals, changing climates, organic molecules, evidence of environments that may once have been suitable for life. Yet beneath all these achievements remains a profound uncertainty. How much do we truly understand about the red planet? The answer is both encouraging and humbling. We understand Mars better than any world beyond Earth, but compared with what remains unknown, our knowledge is still remarkably incomplete. Perhaps the greatest unanswered question concerns life. Not human life, not future settlers. The possibility of life that may have existed long before humanity ever looked toward the planet. Ancient Mars appears to have possessed many ingredients associated with habitability. Liquid water existed on its surface. Organic molecules have been detected. Energy sources may have been available. Certain environments may have remained stable for long periods. On Earth, where these conditions exist, life often emerges. But whether Mars ever crossed that threshold remains unknown. The difficulty lies in the evidence itself. Mars has preserved ancient landscapes, but time has also transformed them. Radiation has altered surface materials. Chemical processes have modified minerals. Billions of years have passed since the environments most favorable for life existed. If ancient organisms once inhabited Mars, their traces may be subtle: a fossilized microbial structure, a chemical pattern, a microscopic mineral arrangement, a molecular signature. Finding such evidence requires extraordinary care. Scientists must also avoid a common mistake. Not every unusual chemical feature is biological. Nature creates complexity without life. Certain minerals form intricate patterns. Organic molecules can arise through non-biological chemistry. A convincing discovery must eliminate alternative explanations. This is why sample return missions are considered so valuable. They would allow researchers to study Martian materials with instruments and techniques unavailable on the planet itself. The search for life therefore continues, not because scientists expect an answer, but because Mars represents one of the most promising places to investigate one of humanity's oldest questions. Are we alone? Another major uncertainty concerns human health. We know that spaceflight affects the human body. We know that radiation exposure increases beyond Earth's protective environment. We know that microgravity causes measurable changes, but Mars presents a combination of conditions never experienced by humans for extended periods. Reduced gravity, elevated radiation, isolation, limited medical resources, artificial environments. These factors interact. The human body is not a collection of separate systems operating independently. A change in one area influences another. For example, reduced gravity affects muscles and bones. Those changes influence movement and physical ability. Radiation may affect cellular processes. Isolation affects psychology. Psychological stress can influence sleep, immune function, and decision-making. Scientists can study each factor individually. Predicting their combined effect over decades remains far more difficult. This uncertainty becomes especially important when considering families and future generations. The first astronauts on Mars would be carefully selected adults. They would understand the risks. They would receive extensive training. They would return to Earth, at least in principle. A true settlement introduces different questions. Would pregnancy be safe? Would children develop normally? Would human biology adapt over generations? Could medicine compensate for environmental differences? No existing evidence provides complete answers. The uncertainty is not a technical inconvenience. It is one of the central scientific challenges of establishing a permanent population. Resource independence represents another frontier of uncertainty. The basic ingredients appear available. Mars has water ice. The atmosphere contains carbon dioxide. Minerals exist within the soil. Energy can potentially be produced through solar and nuclear systems. But recognizing resources is different from exploiting them at civilization scale. Earth's industries developed over thousands of years. They rely on enormous networks of mines, factories, transportation systems, skilled workers, and accumulated knowledge. A Martian settlement would need to recreate these capabilities under severe constraints. How quickly could that happen? No one knows. Automation may accelerate the process. Artificial intelligence may reduce the need for human labor. Advanced manufacturing may allow settlers to create tools from local materials. But every technology has limits. Machines eventually break. Software requires maintenance. Manufacturing systems require replacement components. A truly independent settlement must eventually create the tools needed to create the tools. This concept, sometimes called technological recursion, represents one of the deepest challenges of remote civilization. Another unknown concerns economics. Space exploration has always been expensive. Human missions to Mars would require enormous investments. The scientific benefits are significant. The technological developments may prove valuable. The inspiration generated by exploration may be difficult to measure, but whether a permanent colony can sustain itself economically remains uncertain. What industries could realistically support millions of kilometers of distance? What resources would justify the cost of transportation? Would settlements depend primarily upon scientific research, tourism, manufacturing, communication, or something not yet imagined? The answers remain speculative. No previous society has operated under these conditions. There is also uncertainty surrounding the ethical dimension of colonization. Mars is not an empty stage. It is a world with its own history. If life ever existed there, even in microscopic form, human activity could affect it. Planetary protection policies attempt to balance exploration with preservation. Spacecraft are carefully sterilized. Sensitive regions may receive additional protection. Yet as missions become more ambitious, these questions become increasingly complex. How much exploration is appropriate? At what point does scientific investigation become environmental alteration? Does another world possess value independent of human use? These are not questions that physics alone can answer. They require philosophy, ethics, and international discussion. Even the long-term future of Mars remains uncertain. Some researchers envision gradual expansion. Small settlements become larger communities. Technology improves. Dependence upon Earth decreases. Others argue that the physical challenges may prevent Mars from ever supporting a large independent civilization. The evidence does not yet decide between these possibilities. A careful scientific approach accepts that uncertainty. There is a temptation, especially when discussing the future, to choose a dramatic conclusion. Either Mars will become humanity's second home, or it will become a failed dream. Reality is likely more complicated. The history of exploration rarely follows simple paths. Antarctica did not become a new continent of permanent cities. The ocean floor did not become a second civilization. The moon did not become a settlement despite the achievements of the Apollo program. Yet each frontier transformed knowledge and technology. Mars may follow its own unexpected trajectory. Perhaps it will become a permanent settlement. Perhaps it will remain primarily a scientific outpost. Perhaps it will serve as a stepping stone toward destinations beyond. Perhaps it will teach humanity lessons more valuable than settlement itself. At this stage, the most honest answer is that we do not know. And that uncertainty is not a weakness of science. It is one of its defining features. Science advances because it recognizes the boundary between what has been demonstrated and what remains unknown. Mars sits directly on that boundary. It is close enough to explore, distant enough to challenge us, familiar enough to inspire dreams, alien enough to reveal the limits of our assumptions. The unanswered questions surrounding Mars do not diminish its importance. They are precisely what make it valuable, because the next discoveries may not simply tell us whether humans can live there. They may reveal something much larger. They may show us what makes any world capable of supporting life and the fragile complexity we call home. To reach that frontier, however, humanity will need more than better rockets. It will need better understanding, and that is where the future of Mars exploration truly begins. Every frontier in human history begins with a question. How far can we go? What will we find out? What challenges await beyond the familiar? For Mars, these questions have guided exploration for generations. But as our understanding has grown, the nature of the frontier has changed. At first, the challenge was simply reaching another planet. Then it became understanding that planet. Now the frontier lies somewhere deeper. Can humanity create a lasting presence beyond Earth without fully understanding the complex systems that make Earth habitable? This question sits at the edge of modern science. Not because we lack imagination, not because we lack ambition, but because Mars represents an environment where every assumption must be tested against reality. The next decades of exploration will likely focus on reducing uncertainty. Future spacecraft will continue examining the atmosphere, geology, and potential resources of Mars. Improved orbital instruments may provide more detailed maps of underground ice. Advanced rovers may explore regions never before reached. Same return missions, if completed, may reveal whether ancient Martian environments contained evidence of past life. Human missions, if eventually undertaken, will transform Mars from a distant object of study into a place where people directly experience its environment. Each step will answer questions. Each step will also create new ones. This is the pattern of exploration. The unknown does not disappear. It becomes more precise. One of the most important future developments may come not from a single discovery, but from the gradual improvement of closed-loop systems. A permanent settlement depends upon the ability to recycle. Water must be recovered. Air must be regenerated. Waste must become a resource. Materials must be reused. On Earth, civilization often operates through movement. Resources are extracted, transformed, consumed, and replaced through enormous global networks. Mars requires a different philosophy. Nothing can be treated as unlimited. Every resource has value. Every kilogram matters. In this sense, Mars may represent not only a technological challenge but also a test of efficiency. The technologies required for survival there may teach humanity new approaches to resource management on Earth. However, solving engineering problems does not automatically solve biological ones. The human body remains one of the greatest uncertainties. Space medicine has made remarkable progress. Astronauts have lived in orbit for months. Researchers understand many effects of spaceflight. Countermeasures continue improving. But Mars is not simply a longer space station mission. It introduces a new environment. A person traveling to Mars may spend many months in deep space before reaching the surface. Then they may spend years living beneath reduced gravity. The combination has never been experienced. Future research may reveal unexpected challenges. It may also reveal unexpected adaptability. Human biology has always responded to environments. The question is not whether humans change. They do. The question is whether those changes remain compatible with long-term health. Another frontier involves planetary engineering. The idea of transforming Mars continues to attract attention because it represents one of the largest possible projects humanity could attempt. Yet the scientific challenges remain enormous. Changing a planet's climate requires manipulating systems operating at planetary scale. Earth's atmosphere contains trillions of tons of gases. Its oceans contain vast reservoirs of heat. Its climate is influenced by complex interactions between atmosphere, oceans, ice, geology, and life. Mars lacks many of these stabilizing systems. Even if future technology could warm regions or increase atmospheric pressure locally, transforming the entire planet would require capabilities far beyond current engineering. This does not mean planetary engineering should never be studied. Research into these possibilities improves understanding of planetary climates. It reveals the limits of technology. It forces scientists to examine what makes Earth different, but it remains firmly within the realm of speculation rather than an established plan. The deeper question may not be whether Mars can be changed. It may be whether changing Mars is the best use of human effort. This leads to a broader consideration. Humanity has limited resources: time, energy, scientific attention, economic investment. Every choice creates an opportunity cost. A mission to Mars is also a decision not to invest those same resources elsewhere. Some argue that building a second civilization is essential for long-term survival. Others argue that protecting and understanding Earth should remain humanity's highest priority. This debate cannot be resolved by science alone. Science can describe possibilities. It can estimate risks. It can reveal consequences. But deciding which futures are most valuable requires human judgment. Perhaps the most profound frontier is not technological. It is philosophical. For centuries, exploration has often been driven by expansion. New lands, new resources, new opportunities. Mars challenges us to reconsider what exploration means. Does reaching another planet require transforming it, or can exploration itself be valuable? Can humanity become a spacefaring civilization while still recognizing the uniqueness of the planet that created us? These questions extend beyond Mars. They apply to every world humanity may someday visit. The galaxy contains billions of planets. Some may contain oceans beneath ice. Some may possess atmospheres unlike anything in our solar system. Some may exist in environments we cannot yet imagine. If humanity eventually reaches these places, the lessons learned from Mars will become essential, because Mars teaches a fundamental truth. A planet is not merely a collection of resources. It is a complex system. Its atmosphere, its geology, its climate, its chemistry, its history, all are connected. To live on another world, we must first understand worlds themselves. Modern astronomy is approaching this boundary through increasingly powerful tools. New generations of telescopes will examine distant planetary atmospheres. Advanced spacecraft will explore moons and asteroids. Gravitational wave detectors will reveal hidden cosmic events. Computer simulations will continue improving our understanding of planetary evolution. Every discovery will expand the map of what is possible. But some questions may remain beyond easy answers. Can life truly flourish away from Earth? Can intelligence create a sustainable civilization in an environment where nature provides almost nothing? Can technology reproduce the stability of a planetary ecosystem? Can humans become inhabitants of multiple worlds without losing appreciation for the one that gave them life? These are not only scientific questions. They are questions about civilization itself. The future of Mars will depend on decisions made by people who may live decades from now, with technologies that do not yet exist. They will inherit discoveries from today's scientists. They will inherit the lessons of every spacecraft sent across the space between planets. They will inherit both the dream of Mars and the evidence that challenges that dream. Perhaps humanity will eventually build cities beneath the Martian surface. Perhaps those cities will remain small research communities. Perhaps Mars will become a training ground for journeys much farther into the solar system. The future remains open. What science can provide is not certainty. It provides a clearer understanding of the choices before us. And that may be the most valuable discovery of all, because the greatest danger in exploration is not failure. It is misunderstanding. A dream becomes dangerous only when it ignores reality. Mars does not ask humanity to abandon ambition. It asks humanity to approach ambition with knowledge. The red planet has already given us something extraordinary. It has shown us how rare a living world can be. It has revealed the fragility of planetary environments. It has expanded our understanding of what it means for a planet to be habitable. And perhaps most importantly, it has reminded us that exploration begins not with leaving home, but with understanding home. As we reach the edge of what science currently knows, one final reflection remains. The question of Mars was never only about another planet. It was always about humanity itself. When humanity first looked toward Mars, we saw a possibility, a distant world beneath the familiar sun, a place with mountains, valleys, seasons, and landscapes that seemed to echo our own. For generations, the red planet represented a question written across the night sky. Could we go there? Could we live there? Could we one day call another planet home? After centuries of imagination and decades of exploration, our understanding has become far more detailed. Mars is no longer simply a mysterious red point of light. It is a world with a history, a world that once held rivers, a world that may have possessed environments capable of supporting life, a world shaped by geological forces that slowly transformed it into the cold desert we observe today. It is close enough to explore, yet distant enough to challenge every assumption we carry from Earth. And perhaps that is why Mars remains so compelling. It is not a perfect second Earth. It is something more valuable. It is a reminder that planets are not guaranteed to remain habitable, a reminder that the conditions supporting life are not created by a single factor, but by countless systems working together across immense stretches of time. The atmosphere above our heads, the magnetic fields surrounding our planet, the oceans covering its surface, the geology beneath our feet, the living organisms that transform and maintain the environment around them. Together, these systems created the world we know. Mars reveals what can happen when those systems evolve differently. But this does not mean Mars is a warning that humanity must never leave Earth, nor does it prove that settling Mars is impossible. Science does not support either extreme conclusion. The evidence suggests something more subtle. Human beings may eventually establish a presence on Mars. Technology may continue improving. Life support systems may become more reliable. Robotics and automation may reduce many challenges. Future generations may develop solutions that seem impossible today, but achieving this will require patience, careful planning, and a willingness to recognize the difference between aspiration and reality. The permanent settlement on Mars would not be the discovery of a waiting paradise. It would be the construction of a completely new environment, a place where every breath is engineered, every resource is managed, every mistake carries consequences. The achievement would not be transforming Mars into Earth. The achievement would be learning how to live responsibly on a world that is fundamentally different from our own. And perhaps this is where the meaning of exploration changes. The first explorers crossed oceans not because they believed distant lands were simple replacements for their homes. They went because discovering something unknown expanded human understanding. Mars offers that same opportunity on a planetary scale. It allows us to study how worlds are born, how they change, and why some remain capable of supporting life, while others become silent landscapes. In studying Mars, we are also studying Earth. The ancient riverbeds on Mars remind us of the importance of water. The lost atmosphere reminds us of the delicate balance between a planet and its surrounding space. The empty landscape reminds us that habitability is not permanent. It is something precious, something that must be understood, something that must be protected. The dream of Mars therefore leads us back to a question that existed before rockets, before telescopes, before space exploration itself. What makes a world a home? Is it simply a place where humans can survive, or is it something deeper? A home is not only an environment that keeps us alive, it is a place shaped by billions of years of history, a place where life has created connections between oceans, forests, atmosphere, soil, and countless organisms. A place where humans developed, not as visitors, but as participants in an ancient planetary story. Mars may one day become another chapter in that story. But Earth remains the first chapter. The only world we know where oceans move beneath clouds, where forests transform sunlight into living matter, where countless species share a complex web of existence, and where a thin atmosphere protects everything that has ever looked upward and wondered what lies beyond. Perhaps the greatest lesson Mars offers is not that we should leave. Perhaps it is that we should understand. Understanding does not diminish ambition. It strengthens it. A civilization capable of reaching another planet must first become a civilization capable of caring for the planet it already inhabits. The future of Mars will be written by explorers, engineers, scientists, and generations yet unborn. They may build habitats beneath alien skies. They may discover ancient traces of life hidden within Martian rocks. They may create technologies that allow humans to survive far beyond Earth. Or they may discover that Mars is more valuable as a scientific frontier than as a permanent settlement. All of these possibilities remain open. The universe rarely provides simple answers. Instead, it offers deeper questions. Mars began as a dream of escape, but after decades of exploration, it has become something more profound. A mirror. A world that shows us both the possibilities of human ingenuity and the limits imposed by nature. A place that teaches us how difficult it is to create a home, and how extraordinary it is that we already possess one. Beyond the horizon of Mars lie countless worlds, still waiting to be explored. Planets around distant stars, moons beneath frozen oceans, regions of space where the laws of physics reveal mysteries we have only begun to understand. Humanity will continue looking outward. Curiosity is part of who we are, but wherever we travel, Mars will remain a reminder that exploration is not only about reaching farther, it is about seeing more clearly. The Red Planet does not simply ask whether we can live somewhere else. It asks whether we truly understand what makes life possible, anywhere at all. And after all our discoveries, one question remains quietly waiting at the edge of knowledge. If a planet as similar to Earth as Mars could become a frozen desert, what hidden conditions are we still overlooking that make our own world so remarkably alive?